in your notebook, open to a new page, entitle it 8.2, the Pythagorean Theorem, and its converse. Now you remember Pythagorean Theorem from previous years, and we've used it in class before. Today we're going to do a brief review of it and then use some more properties of the Pythagorean Theorem to solve problems. So as a recap or a recall of what the Pythagorean Theorem is, the Pythagorean Theorem states that given a right triangle, so for instance if we draw in our notes here a right triangle and label the legs, the length of the legs A and B, and the length of the hypotenuse C, then we know C squared is equal to A squared plus B squared. And that was shown in that first video that you watched, that proof without words. So we have used this a lot in some problems, and we're not going to do any really as reviewed together right now. Instead, we're going to jump ahead to what we call a Pythagorean triple. So a Pythagorean triple is a set of three non-zero whole numbers, A, B, and C, such that C squared equals A squared plus B squared. So essentially it's just three lengths of a right triangle that are all whole numbers. Because if it's a right triangle, it has to satisfy the Pythagorean theorem. So we have some common Pythagorean triples. So we're going to make a little chart of common Pythagorean triples. And the first one we have is the 3, 4, 5 triple. So the 3, 4, 5 triple says, the legs have lengths of 3 and 4, the hypotenuse has the length of 5. So any triangle with side lengths that are multiples of 3, 4, and 5 make a perfect Pythagorean triple. So for instance, 6, 8, and 10 if we multiply them by 2. Or 9, 12, and 15 multiplying by 3. So given any number x, if it's this perfect Pythagorean triple, then it would be 3x, 4x, and 5x for those lengths. The second set of Pythagorean triple is the 5, 12, 13 triangle. So again, we can double the side lengths and get 10, 24, and 26, and you'll end up with a Pythagorean triple. Triple them to get 15, 36, and 39, or just say for any value x. When multiplied by this set of numbers, you get a Pythagorean triple. So 5x, 12x, and 13x. The next common Pythagorean triple is the 8, 15, 17 triple. So we're going to use that same pattern. We'll double it. We get 16, 30, and 34. We'll triple it, get 24, 45, and 51. And then just say for any value x, you have 8x, 15x, and 17x. And our last Pythagorean triple set is 7, 24, 25. So these are given, again, doubled. We get 14, 48, 50, and then tripled, 21, 72, 75. And given any value x, the triple is 7x, 24x, and 25x. So take any one of these Pythagorean triples. Let's take, let's take 15, 36, 39, and test it. To show you that it really is a Pythagorean triple. So the Pythagorean theorem states C squared equals A squared plus B squared. So what we know is that the hypotenuse, let's write this down, the hypotenuse is the longest side. It's also across from the right angle. Okay, so we grab the longest side, in this case that's 39, and replace c with 39, and set it equal to the sum of the squares of the legs, so 15 squared plus 36 squared. Okay, so what we had before was 39 squared equals 15 squared plus 36 squared. When you plug those numbers into your calculator, you get 1,521 equals 225 plus 1,296. So let's apply, or when you add those, you get 1,521, which those two are equal, so it has to be a right triangle, which we know because it's a perfect Pythagorean triple. So let's use Pythagorean triples to solve problems. So if you're given a problem involving a right triangle that has Pythagorean triples, you can use them to solve. So for example, if I have a triangle, a right triangle, with one leg equal to x, the other is 12, and the hypotenuse is 15, I can use Pythagorean triples to help me solve this fairly quickly. You could use Pythagorean theorem still, but with Pythagorean triples, you don't have to. So looking at our common Pythagorean triples chart, do I have any that are already listed with a hypotenuse of 15? So looking through, I see right here, we have a hypotenuse of 15, and one leg is 12. Well, that forces the other leg to be 9, so x here has to equal 9. So that one's nice because it comes right off of our chart. Let's try another one. So problem 2. This time we're going to have the hypotenuse be the value of x. So we draw a quick right triangle. The hypotenuse has a length of x. One leg is 48 and the other one is 20. So again, I'm going to see first, can I find a Pythagorean triple that I already have with legs that have lengths of 20 and 48. So as I look through at the legs, I don't see that. I got close. This was close to that, but I don't quite have it. So what I'm going to start doing is testing. So I'm going to test the 3, 4, 5 Pythagorean triple first because that tends to be the most common one. Not always, but in this case it tends to be. So I'm going to take 48, which would be kind of the middle length. This would be the smallest. The hypotenuse is always the longest, so this would be the middle. And divide it by the middle length on the 3, 4, 5 triangle. So I'm going to divide that by 4. And 48 divided by 4 gives us 12. Now, when I take 20 and divide it by, in this case, that would be 3, do I get the same number? When I take 20 divided by 3, no, I'm not going to get 12. So it can't be a 3, 4, 5 triangle. So let's test another Pythagorean triple. Now I'm going to test the 5, 12, 13 triangle. So I start with 48, the middle length. I divide that by the middle length on the 5, 12, 13 triangle. So I divide that by 12, and I get 4. Then I'm going to take 20, the short length, and divide that by the short length on this triple, which is 5. And again, I get 4. So that means I have a 5, 12, 13 Pythagorean triple on this. My multiplier was 4, so I take 13 times 4 to get the length of the hypotenuse. And when I take 13 times 4, we get 52. So x is equal to 52. Okay. Last example of this, and this one I'm going to have you actually work on your own. I'll have you pause the video. So in this one, we have a triangle. Again, of course, a right triangle. One of the legs has a length of x. The other one is 14. And then the hypotenuse is 50. So go ahead and pause the video, see if you can solve this using Pythagorean triples. Okay, so we should have gotten x is equal to 48. It was fairly quickly solved if you used your chart up here, it was already given to us. All right, let's move on. So Pythagorean triples are very useful because they help us solve problems a little bit quicker, or they tend to. But what's even more useful about the Pythagorean theorem is its converse. So its converse states, if c squared equals a squared plus b squared, then you have a right triangle. So let's write, we use these in Pythagorean inequality theorem. So let's write these out. The Pythagorean inequality theorems. So one of them is just the Pythagorean theorem. This isn't really an inequality theorem. We know that c squared equals a squared plus b squared. If that's true, then we have a right triangle. Okay, the first inequality theorem says if c squared is less than a squared plus b squared, then you have an acute triangle. And the final inequality theorem states if c squared is greater than a squared plus b squared, then you have an obtuse triangle. So one thing we have to note here is that c, so let's write a little note, c is equal to the longest side every time. And that's, after that, everything else kind of falls into place. So let's look at a couple examples of this. I'm going to shove these papers up and give us some space. Yeah. Okay. So here's our examples. So the directions would say, classify the triangle as right, acute, or obtuse. So here's our first one. Side lengths of 14, 8, and 25. So what I do is I first identify what the C value would be. In this case, that would be 25. And I know I want to compare 25 squared to the sum of 14 squared and 8 squared. So having a calculator handy is going to be necessary in this case. Okay. All right, so 25 squared gives us 625. 14 squared gives us 196, and 8 squared is 64. So I add the squared leg lengths, and we get 260, which is less than 625. So in this case, it is obtuse. Okay. Next example. So here we have 24, 8, and 18. So looking at this, I can see that 24 is going to be C. So I take 24 squared and compare that to 8 squared plus 18 squared. Well, 8 squared is 64. I can write that down right away. 18 squared gives us 324. And 24 squared gives us 576. When I take 64 plus, what was it, 324, we get 388. I compare that to 576. This is greater, so it's obtuse. Now I just remembered, let's look back at this example here again. Let's determine if it was even a triangle, because I'm pretty sure this one doesn't work out that way. So remember to see if a set of side lengths makes a triangle, you add the two smaller ones, and it has to be greater than the longest side. So in this case, when I take 8 plus 14, I get 22, which is less than 25, so it's not a triangle. So in this case, it's not even obtuse, it's not a triangle, it's nothing that we need to worry about. Okay, example 3, side lengths of 7, 10, and 12. So in this case, let's test to make sure it's a triangle first. 7 plus 10 is 17, which is greater than 12, so we're good. I know C is going to be equal to 12, so I want to compare 12 squared to 7 squared plus 10 squared. So this is 144. 49 plus 100. So we're comparing 144 to 149, which 144 is less than that. So this is an acute triangle. Oh, I'm sorry, you didn't see that. But we do get an acute triangle here. All right, next one we have is 75, 72, and 21. So again, C is going to be the longest length. In this case, that's 75. So I take 75 squared and compare that to 72 squared plus 21 squared. I do not know these off the top of my head. Okay, so 75 squared gives us 5,625. 72 squared is 5,184, and 21 squared is 441. So I add that to 5,184, and we get 5,625. Compare that to 75 squared. They're equal to each other, so that means this is a right triangle. Okay. So on these next two, go ahead and write them down and then try them out on your own. You can pause the video to try them out. So this example 5, you're going to have side lengths of 16, 7, and 23. And number 6, side lengths of 10, 10, and 10. Go ahead, pause the video, work those ones out. Okay, on number 5, it's not even a triangle. In this case, when we take 16 plus 7, you get 23, which is not greater than the longest side of 23, so it's not a triangle. On number 6, when you classify this one, you get an acute triangle. And you can even classify this one without doing the work, because if all sides are equal, it's an equilateral triangle, which means it's automatically an acute triangle because all angles would be equal to 60 degrees. All right, last example here. So on this example, we're going to solve for x and then put in simplest radical form. So all that work we did with simplifying radicals, we're going to use in this example. Okay, well, or at least we're going to use them in this example and then in some of your homework problems too. So we have a triangle. We don't know the length of the hypotenuse, so let's call that length x. The legs have lengths of 3 square root 2 and 4 square root 2. So looking at this triangle, I want to first test to see if it's a Pythagorean triple. And we'll actually work it both ways, that way in case you forget to do that, it's okay. So take that chart that we had from before, fold it up so we can see. And we can see that it would be a 3, 4, 5 triangle because we take 3 times square root 2, 4 times square root 2. That means x is equal to 5 times square root 2. So if I write this out kind of algebraically here, we've got 3x, 4x, and 5x. Replace x with square root 2. That'd be 3 square root 2, 4 square root 2, and 5 square root 2. So that means the length of x in this case would be 5 square root 2. So don't confuse these x's with this x. They're technically different x's here. Let's use the Pythagorean theorem to solve this one though, because sometimes in your homework you won't be able to use Pythagorean triples. So Pythagorean's theorem states c squared equals a squared plus b squared. In this case, I don't know the hypotenuse, it's x, so I replace c with x squared equals a squared. I'm going to call 3 square roots of 2. I'm going to put it in parentheses so that I remember to square both of those, plus the other leg is 4 square root 2 squared. So simplify it a little bit, we get x squared equals, this squared really applies to both of the factors inside of here. So I'm going to square the 3 and I'm going to square the square root 2, which would give us 9 times 2 plus 4 square root 2 squared is going to give us 16 times 2. So x squared equals 18 plus 32, or in this case, x squared equals 50 when I add those up. So to solve, I take the square root on both sides, so x would equal the square root of 50. And we know how to simplify that, so I'm going to do a little simplifying off to the side. I'm going to use perfect squares to simplify. I know 50 is equal to 25 times 2, so that's the square root of 25 times the square root of 2. Square root 25 gives us 5. So our simplest form is 5 square root 2. So notice again, we got the same answer using Pythagorean triples. Okay, you can now get the worksheet and work on that for the rest of the time.